Thank you everyone for coming. It's kind of an intimate, nice atmosphere. Got like a variety of different interests, so I'll try to make the talk interesting for everyone, but I hope it won't be too boring at some points. For some of you, we'll see how it goes. So I guess there's kind of a weird echo. Let's see. Closer. Wow, I feel really powerful now. Okay. Okay. So what I've done is I've created a MySQL storage engine, effectively, that we like to kind of consider a kind of cloud version of MySQL, and I'll just be going into that now. This, incidentally, is where I studied. It's beautiful Lugano, Switzerland, and I hope you'll also take a chance to visit there if you have the opportunity. Okay. So here's a table of contents, which is probably going to be useful for the people who read this later on, and it's not going to serve much use at the moment. I'm going to go through the typical kinds of things that you go through in a talk. So let's get right down to the problem. What really is a problem with MySQL? At least in our view, the problem with MySQL is that it's fundamentally a standalone database server. So what does this mean? Is that it was architected originally in the 80s and 90s, or it's the inheritance of MySQL is an architecture that was designed primarily in the 80s and in the 90s. And what this means is that it was not designed for the workloads that it's being used for these days. So with the internet came a dramatic growth of demand, and MySQL just was not really prepared for it. But it can be made to scale. This meetup group exists in 2014. It's being used for real-world applications. So somehow it's being made to work. So what really are you sacrificing? Really, you're sacrificing consistency guarantees, deployment flexibility, and basically all of our collective sanity. This is an actual photo from 2008 when I worked as a MySQL DBA. That really is not Photoshop, it really is my actual hair. One of my friends here knows the company I was working for, and I think this was just at one point where I was just going so crazy with all the various problems that this happened. So, you know, we all want MySQL to be easier to use, and we want it to work better, and it's an active research question how you make SQL databases that have an inheritance from the 1980s work for 2010 type workloads. So I guess how would we start with? Everyone I'm sure has heard of NoSQL, or NoSQL is kind of something that is a big sort of buzzword at this point. Where did NoSQL come from? At least in my view, NoSQL is really sort of kind of an outgrowth of the problem that you were applying databases like MySQL, Oracle, to very, very different types of systems. So transactional systems, data warehousing systems, geospatial databases, front-end databases, and so on and so forth. So eventually this problem became so big, you had sort of a revolution that became sort of known as NoSQL. But really, NoSQL is kind of, in my opinion, not a very good word to describe what happened, because SQL never really was the problem. The problem was using a kind of one-size-fits-all architecture, one-size-fits-all approach to solving a wide variety of different problems. So I guess we can talk a little bit about how actually MySQL gets used to scale systems in the real world. I guess for my purposes, I like to consider MySQL scaling approaches in sort of four categories. Four categories meaning how you can take MySQL away from its single server inheritance and scale it out to multiple servers. Because a trivial, by the way, anytime I put a little star here, it means that there's some notes in the presentation. If anyone's interested, you can come to me later. So trivial would be you just buy a bigger server. So I think that's not very interesting for us. So how do you get MySQL to scale to more than one server? So in general, you have the basically just replicate. So MySQL comes with replication out of the box. It works relatively well, but it doesn't give you very good consistency guarantees. Similarly, you can shard or horizontally partition, which is also done a lot in large-scale settings, which is basically chopping your data up into pieces or servers and then routing your transaction accordingly. Two more interesting approaches are basically inserting something between MySQL and your client, or inserting something in between MySQL and some other mechanism. So basically, I mean, this is just sort of a visual view of what I just discussed. Effectively, what gets done for replication, you have a master, and then you replicate out all the transactions to a known number of slaves. All of your update transactions go to this first master, and then let's say these slaves are used to handle read-only transactions. So this works relatively well, and I also should mention that these are not necessarily mutually exclusive. So you can merge this, with this approach, where now you shard all of your data onto servers that have only a portion of the data set. So I won't talk too much about sharding. There are lots of talks and papers and stuff that you can read about this. I just want to sort of present sort of general approaches that you can take. Another interesting approach to scaling out MySQL is the idea of putting some kind of middleware in between the clients and the actual data nodes. This isn't exactly, so you could consider this to be similar to the idea of sharding, except that I think this is being a little bit more sophisticated. And there are a lot of products that are out on the market now. There are too many for me to enumerate that do something similar to this. So effectively, your client connects to this kind of middleware, and then this middleware, with some kind of magic under the covers, might end up writing all your data to a bunch of different machines under below. This could be sub-SQL, it could be any number of different things that they do, but this is just sort of a general kind of view. And then the fourth approach, and this is where I guess our work falls in, would be introducing something kind of underneath MySQL. So this lists sort of three examples here that maybe you might have heard of. MySQL cluster is basically a storage engine that gives you sort of a separate sort of storage infrastructure underneath the server. Our approach falls into that. And then Galera is also interesting because it uses NODB, which some of you have heard of, to do basically a broadcast of updates in a consistent way. A little star here that I pointed out. So Galera, I don't know, has anyone heard of Galera application? One, two, okay. Interestingly, Galera, I don't know if they were directly affiliated with my advisor, but their work basically is kind of like, I guess, sort of an offshoot of my advisor's original research. So this work that we've done is sort of like a new generation of Galera. Okay, so I've talked for a little while, and now I'm going to just talk about what exactly is MoSQL, the system that we've built. Basically, it's a MySQL-based system that gives you strong consistency and elastic scalability. There are two asterisks on this slide, so there's a lot of caveats. I'm not going to go through all of them, but this is a particularly contentious slide, I guess. So basically, our system is not a big data system. This is something that I really want to stress. And so if there's anyone here that's interested in big data, if you want to leave, I will not be offended. But we are explicitly not in a big data system, at least not at this point. Our target, much in the spirit of one of the previous slides, is transaction-type workloads. So if you need a big data system, plenty of people will be interested in selling it to you. And this was done as part of a research project at the University of Lugano in Switzerland with my professor, Fernando Canone, and Daniel Shasha, the guy I worked with. So what does this actually look like when you use it? So we're getting kind of deeper and deeper. Effectively, what you have is, let's say a typical client or a typical application, you might have some kind of a connection pool that connects to your database layer. With our system, what you get is, a MySQL server, or any number of MySQL servers, let's say n of them here. And the database that you connect to, or the database that you see, is completely, or transparently, you see the same view of the database regardless of which node you connect to. And all of this happens with, some magic down here, which we'll discuss in the later slides. But this is effectively what it is. And the idea of scalability or elasticity is that you can remove and add servers to this transparent view of the database. So this is sort of what we define as elasticity. This is actually something that's not quite agreed upon. So different people will tell you different definitions of what elasticity is. This is just to be clear about what we consider it to be, that you can have a running system like a database, or it could be anything, and then you have a number of servers, and then you can transparently and on the fly add a new one, and everything just sort of works sort of magically in theory. Now, why is elasticity a big deal? Why this is something that's kind of a big deal in the database research community? The problem is this. I mean, this is a contrived graph, I admit. I didn't, but effectively, imagine this is your weekly demand curve of some service. Let's say it's a web service, whatever it might be. And most people, I mean, even though the web has allowed applications to be distributed all throughout the world, even if you have a perfectly distributed application all throughout the world, you still have the Pacific Ocean, which is large. So these types of workload variations are I guess, a factor of most applications. So if you have this type of workload, let's say on a daily basis, let's say you buy a server that can handle this amount of demand. This could be widgets per hour of your service, so it could be anything, doesn't really matter, right? So what happens? Let's say if your system can handle 75 transactions per hour, and then now you get 100, it's a peak. So here, you're under provisioned, right? So this is bad because now, you might have a little latency, or so your clients might end up saying, okay, I'm not going to wait for the service anymore, I'm just going to go somewhere else. Eventually, actually, this peak will end up probably tending down towards the system capacity. So you'll end up just losing all of this if you're under provision. So this is a bad thing, and I don't think that this happens too much. But the other problem, which is equally severe, equally problematic, is the fact that if you buy a server to handle this level of capacity, you're basically wasting all of this. And at least in my experience as a MySQL DBA, this is a particularly bad problem because I put this here. I guess anyone that's worked as a database person will probably understand this thing. That no DBA was ever fired for over provisioning a server. So, I mean, these days now with the cloud and all this kind of stuff, instead of saying that if you buy a $30,000 server, you're going to be okay. No one's going to fire you for buying an expensive server. Now it's like a $3 instance per hour. I don't know what's the most expensive. What is the most expensive instance on EC2 now? Like $4 or $5?
About 5 or 6.
5 or 6, yeah. Okay, so no one will fire you for provisioning a $5 server when you could have gotten away with servers. So I hope that this convinces you of why elasticity is at least an interesting thing. And I think that as we start to provision larger and larger servers, this waste will become more and more acute, or we'll be more aware of it. So now to talk a little bit about serializability or consistency. I'm not going to go too much into the details of this, but I hope I can just sort of give you a little bit of a motivation for why this is a big deal. Basically, serializability, when you have strong consistency, your life is made a lot easier because you don't have to worry about anything else. Effectively, you operate on your database as if you were the only one using it, and if your transaction commits, you can assume that everything was okay. So you don't have to worry about, so this client can do his work, and then this client can do her work, sorry to be gender there, and then if both of them commit, you can be sure that the system is consistent, and you don't have to actually put any logic in here saying like, oh, make sure to check if this guy did something weird or whatever. Everything is consistent. This is something that I think a lot of people didn't quite realize was going to be a problem when they got into NoSQL systems like Cassandra or other systems that provide eventual consistency, which is effectively not consistent. Okay, so just some other features of the system. One of the nice things that we also have is the ability to add cache nodes. So this is kind of like fusing the idea of memcache into the server, but also in a consistent way. So what we can do with our system is you can deploy a cache-only node, which doesn't actually own any data, so it doesn't redistribute any data. It can live for a while, handle transaction load, and then you can literally kill -9 it. And everything just sort of works. So we can scale read-only transactions very well. Update transactions are kind of linear, not really linear. We call it linear or sublinear. And because our architecture is very flexible, we can, the architecture is very decoupled, so you can deploy it in a variety of different ways. Effectively, it's an in-memory database, but we have on disk, or we actually log transactions on disk. And there's a configurable level of durability, and here's another asterisk, in case anyone's interested. depending on what kind of guarantees you want, you can tweak the performance. Okay, so we're getting down a little bit more. Basically, so as I said before, you have like any number of MySQL servers that can be in your pool, and then these servers then connect to a storage layer, which is the second tier of the architecture, and then that storage layer is then dependent on a replicated state machine, which is based on Paxos. Who's heard of Paxos here? One. Okay, I guess we can talk offline afterwards. We don't have to go into too much detail about Paxos. So, but this is the basic architecture. And here I just go into the details. This. So I don't know if I'm going to talk too much about Paxos, but basically what you can think of Paxos is kind of gives you this nice primitive for building distributed systems. So it's like saying I have 3 or more servers and I want to get them to agree on some value and to agree on these to agree on that value in a certain order, or to agree on a set of values in a certain order. And if you have this as a guarantee, then you can build really cool stuff on top of it. So in the real world, typically what this means is that you need to have 3 servers, and if one of those servers has Christopher Walken come and take a sword to it and destroy it, your system still should work in theory. If you really need to handle 2 servers, so if you need to fight off 2 different aliens in your data center, and 2 servers are taken out, then you would need to have 5 servers in this distributed lock. Okay, so I can probably skip that. More interesting stuff happens, I guess, in the middle tier here in the storage. So this is actually, we could actually almost market this as a NoSQL system entirely on its own. So the storage layer is effectively kind of like a straightforward Berkeley DB key value database, but distributed. And so the MySQL servers actually connect with TCP to the storage nodes and then do all the transaction work. And then these nodes then decide what stuff to commit and what stuff to abort. This stuff, and then also all of the code, we didn't write MySQL obviously, but the storage engine, this code, and then Paxos, all this stuff is written in C with Berkeley DB, lib event, and message back. Many of those are familiar. Another asterisk here is I'm implicitly implying that this is good because it's written in C. I hope that doesn't offend anyone that's a fan of Java or systems or languages like that, but that's what it is. Okay, so I'm curious, is anyone here familiar with like transactional memory or software transactional memory? Has anyone come across this? I guess the usual suspect is raising his hand. Okay, so I'm wondering how much detail I went into this. So transactional memory is a kind of related idea to what's happening here. It's this idea of doing a whole bunch of stuff and then basically saying, okay, I'm going to just sort of send this and then see if it comes back as being accepted or not. In the software transactional memory area, you have this idea of doing a bunch of work and then committing it and then seeing if it was if the state of memory can be made consistent. We effectively take that same approach here, but within the scope of like a key value kind of database. So essentially, let's say, assume that you had 2 different transactions running, and then I'm just using this basic get put interface. I don't want to talk about SQL at this point. Let's say these are running in parallel. So if transaction 1, gets some value, let's say the balance of some account, and then puts something there, and then tries to commit it, and then this one does it at the same time. What this would mean is that both of these transactions cannot commit at the same time. Or both of them cannot commit and then maintain the state of the system, maintain a consistent state of the system. So then you have some other process, which in our system is basically like a certification layer or certifier that will say, okay, one of these is not going to be able to commit, maybe number 2, and that one will just have to retry. So if this client is doing this work, it would have to basically redo what it was doing. And then this is how, so what this means is we can have optimistic local transactions happening. So this guy does all of his work without any interaction with any other servers on the network. Only at this point, when actually a commit happens, does anything go. So basically, this is optimistic concurrency. It's a typical case of optimistic concurrency control. Does this make sense to anyone? Apart from, okay, good, all right, I guess it did. Okay, and then the top layer is the SQL layer. So this is effectively just MySQL. We inserted our code effectively as a storage engine. And then this storage engine code then connects to the storage layer and then does all of the work of actually inserting and modifying data. These nodes can then be connected to kind of interchangeably. So you could have, for example, one MySQL server that connects to a number of different storage nodes, or you can have a bunch of MySQL servers connecting to one storage node. So this is flexible. There are a bunch of limitations at the moment, which I can discuss in more detail offline if anyone's interested. At the moment, so a table has to have a primary key, and we don't support blob indexes or some fancy features like this. Okay, so this is just sort of a very simple example of like how actually this, how this all works. So, for example, let's say you have, there's a point. Here we go. So, let's say your client decides to connect to this server because it wants to start some kind of a transaction. So it will connect here, and then let's say it wants to retrieve these two values from the table with this primary key. This primary key, most likely, let's say, would be on this particular storage node. So it would retrieve that value immediately back into this layer, and then MySQL, and then that goes up through the storage layer, or through the storage engine layer back to MySQL. Then let's say this SQL statement, which does, let's say, 2 reads from the table. This row might be on a different storage layer. So what happens is that this node, this server will ask this storage node for both of these entries. This one might actually live here, so then this one is retrieved remotely and then sent back, and then sent back up. And then this value then gets cached on that node. So in this way we get data locality. And then the insert also happens locally, so I missed that arrow here. And then at the end, basically the whole state of that transaction gets sent to the certifier and a replicated state machine. And then if it's accepted, it's sent back as an accept. If it can't be committed, it's sent back as an abort. And that's basically it. Okay. How am I doing this time? I didn't bring my watch. I guess we're good. Okay. So basically, there are 2 different types of nodes. So I just want to make it clear, when I say a node, storage node, I mean this thing here. So basically, this is basically a process which contains basically all the data in memory. These storage nodes can be either cache nodes or data nodes. So you can have the system set up in such a way that there are, let's say, 2 data nodes. All the data will be stored on those 2 nodes, and then you can deploy cache nodes, which will cache data temporarily as the data is retrieved, and then those nodes can be killed without really any impact on the system. If you kill a data node, then those values have to be retrieved from the distributed log, so it's a lot slower. But this is a nice thing, because what this allows you to do is to handle workload spikes very, very quickly, on the order of 10, 15 seconds, or as fast as you can load up a virtual machine. So this is one of the things. So I mean, this gets into discussions of how exactly do you start up a server, and if you're working in cloud, what this means is that you can observe, let's say, the demand of your system. If it's starting to get slow, or your company had a commercial on TV, and then you need to respond to a workload spike very, very quickly, you can launch a virtual machine, launch one of these cache-only nodes, handle the workload, and then shut it down immediately after. So now what I've done is I've just got a couple of examples of how you can actually deploy the system. Basically, this would just be a very, very straightforward example where, let's say, you have 2 nodes in your system, and they have just some block of memory. It could be 4, it could be 40. It's not really that important. And then if you want to sort of offload these nodes from some of the burden of handling transactions, you can launch 2 cache nodes. And then these ones will then cache any data that they've retrieved, and then and send updates back to the real nodes that hold data. Another architecture, we call this kind of like the memcache style architecture. It's interesting because it's consistent. So what you can do is you can have let's say, a series of cache servers which have MySQL on them, and they actually handle the load from the clients. The actual data owning nodes would then not be actually touched. They would just be responsible for retrieving or for storing the updates that happen on these nodes here. And then these ones would then presumably be relatively static. These ones you could add and remove depending on the workload. I have some performance graphs here, but I don't know how much we'll go through these. But effectively, these are graphs that we have from the original paper. So I should stress this is not exactly what you would get with the version that we've open sourced, because this was done on a multicast-based distributed, but yeah, it's not. Effectively, what this illustrates, I know this graph's a little bit odd, but I'll try to explain it. What we're trying to show here is, let's say you have a system which is using InnoDB, just standard InnoDB on MySQL. And then let's say you're doing something like TPCC, which is like this kind of warehouse ordering kind of benchmark that's supposed to be relatively representative of a typical application. So let's say you have only a certain amount of memory on your server, and let's say you load 10 warehouses. So these warehouses can be fairly big. They store about anywhere from 200 to 300 megabytes per warehouse. So let's say your server is relatively small. On InnoDB, when you load 10 warehouses, your throughput is fairly good. But then as the size of your database starts to outstrip the amount of memory that you have on that server, the performance tends to go down rather quickly. And then once you get to a point where you have 160 warehouses, let's say, and then you're way beyond the amount of memory that you have in the system, the performance really goes right, almost down, basically. Whereas with our system, so we, mostly because the code is not fully optimized for various reasons, we're a little bit slower at this point. But then as you need to scale out, you can just continue adding servers, and then you can get performance that's way beyond what you could get with a single server. And then this just sort of shows the effect on latency, which I think I'll just skip. Another interesting thing, so this was one experiment we ran where we had 4 and 8 nodes, and then so here you can see what happens when, so here we showed like the amount of cache requests there were. So when you start up these nodes, they end up retrieving a lot of data which is common and caching it. And then you can see here the performance is relatively low, and as the number of cache requests goes down, performance tends to go up, and then this sort of stabilizes over a period of time. Future work, I think I would need 4 slides for this, and there are really a lot of things I would like to implement. But at the moment, it's just whenever I manage to get time to actually work on the code, I tend to add stuff. The main thing that really I'm trying to focus on now is tighter integration with cloud platforms, because I personally think that this is very an area where cloud platforms lack. An area where cloud platforms are lacking is in integration with databases that are elastic and scalable, like what our system provides. So I really would like to focus on this, and then just making it actually work. And these sorts of things, in a relatively easy way. So how do I get it? This is also a good question. I would still consider the quality of the code to be alpha. So please don't, even if you do manage to get it running on your own, don't put your financial records in there and then expect these things to be kept safe. I'm in progress of refactoring and improving a lot of stuff in any case. But if you are interested, there is a README on our Bucket repositories where you can actually attempt to build and install it. And I'm actually working on making some VM images available on various cloud platforms to make it a lot easier to try it. And then this is just more info, my email address is here, and I think I'll post this presentation to the actual, meetup group. So in case anyone's interested in seeing some of the links that I've had here, you'll have access to that. And I have a screencast also as a link in case anyone's interested. And that's pretty much all that I have. I mean, I have a lot more slides in my appendix in case someone's interested, but that's all I have really that I wanted to talk about today. So if you have questions, comments, curiosities.
So did you ever look into scalability The system architecture is very, very similar to what you described.
You know, I tried my best to read up on as many of these systems as I could, but I knew that eventually someone would throw one at me that I was not familiar with. I might have read about it at some point, but I'm not entirely familiar. So scalability is one word.
It's a storage engine.
Oh, for MySQL. I think I wrote a blurb about this in one of my related work, but I don't remember the details of it. We can talk offline. I'll look in some of my notes, and I might.
And the other one is MySQL cluster, actually.
Okay, so that's a.
MDB is very similar in nature to your design.
So MySQL cluster, if that's a good question. I have. Let's see. Maybe I'll go back, way back. So the difference with MySQL cluster, actually I can show it to you here. The two most important differences are that MySQL cluster doesn't give you serializability. So your consistency guarantees are way worse. So I think the last I checked, MySQL cluster only gives you read committed. So you just know that what was read has been committed at some point, but then you don't have any real isolation. So you lose basically the ease of development that you get by just knowing that all of your stuff can be thought of as being run on a single, as being run like a serial. The other big thing, at least the last I checked, is that MySQL cluster doesn't give you sort of transparent sort of elasticity. So you can't just add and remove nodes, and you definitely don't have the idea of cache nodes. The last that I checked. So it's definitely similar. It's a different. That's also why I stressed in this one here that, in a sense, it's the same that they've implemented a storage engine with a separate storage layer underneath the covers, but our system is really, it's like comparing, I don't know, like, well, I don't want to say anything bad about MySQL cluster, it's just, the guarantees are much weaker. That's the added features. But it's a robust, mature product, so I'm not claiming that our system is stable or that you should use it in favor of MySQL cluster today, but I forgot, so scalability is the other question that I ran.
There's about 50 different products that I can think of that have aspects that we talked about. But
yeah.
ScaleDB is just the one that is very, very, very similar. So they got about 4 years head start in terms of development. So
I think, yeah, I mean, that's partly why. I mean, I had actually, no, I don't have it on this one. I had on my other presentation that I gave to an academic thing, had I think 4 slides of different systems that offered different sort of things. I think the one difference, at least with our approach, is that we're being relatively open, and so all this is open source, and we're not really trying to advertise it as being some kind of solution to all the world's problems. But there are different approaches. So I think a lot of the solutions that are out there, so I mean, tend to be more middleware oriented. So one that comes to mind, I think there's Clustrix was one solution that I just read about not so long ago. And effectively, their approach is almost taken straight from this paper that my advisor wrote like 6 years ago. So it's just sort of a middleware that sits in between the clients. It's sort of this middleware orchestrates all the transactions for you, and then you have this kind of nice view of the database from that. Then there are also a bunch of solutions.
But instead of a distributed system, you're relying on a hardware solution there that handles state management. So you're using an InfiniBand network for low latency distribution of blocks in the storage system.
This is for a cluster?
Clustrix is less sophisticated than what you described.
Okay, maybe, I don't know. Sorry, I could be even confusing because they're really, like you said, 50, I lost count, I can't keep track of them. And then a lot of them sort of fall off the radar as quickly as I learn about them. Many of them sort of disappear. So another interesting one was, I don't know how to pronounce it, Z-Round or XE-Round.
Z-Round.
I think they just sort of disappeared at one point.
Yeah, they ran out of money.
They ran out of money, yeah. So, I mean, they, in a way, at least from what I can tell, I tried to read the patent, but reading a patent is a whole different thing from reading a scientific paper. Because it seems like with a scientific paper, at least you're trying to be honest about what you're doing, you're trying to make it easy to understand, whereas I feel like with patents, it's just almost like, or at least in my opinion, it seemed almost like they're trying to make it harder for you to understand what's going on. Or maybe I'm just not used to the type of language that they use. But to read a distributed system with patent is not fun. Let's just put it that way.
Nothing that they ever wrote down is easy to understand.
Yeah. But yeah, I think I never actually managed to figure out exactly what T-Round did, but I assume it was something similar to this fourth approach.
It's an in-memory replica.
Yeah, I don't claim to be an expert in knowing exactly what they do. So yeah, there are a lot of products. If you're a user of one of these systems, I won't envy you to try to sort of sort out which ones are good and which ones are bad. It's a hard problem. There's a lot out there. But I think that hopefully in time, some relatively mature products will eventually sort of sift out of this kind of primordial new SQL ooze, and we hope to be one of those, at least to be an open system that people can still play around with. So even if we run out of money, the code is there. You know, not that we ever had any money in the first place. Okay, any other questions?
How would you characterize success of your project? What would you say, if you were to achieve something, what would you consider successful?
Well, that's a good question. I mean, from an academic point of view, it's already successful because it was already published. So in a sense, it's been validated from a sort of scientific point of view. Success, I mean, I like writing, like building stuff, you know, so I would like people to use it, personally. But then that has to be balanced with this need to eat and make money. So, you know, there's always these competing factors. Yeah. I mean, I would like that there would be a MySQL event every night so I could come and eat great pizza every day, but then I don't know, I would be just making talks every, you know, in attendance. You know, so I mean, in the end, people that want to write cool software tend to have to find a way of financing it. And it's just sort of a reality, I think, in the world as it is today.
Any other questions?
Anyone else?
Anyone?
So you, for those of us who aren't crazy into DBA architecture, you mentioned 4 different overall like systems for how you can scale MySQL. Can you give like examples of like where those different types of architectures are actually used?
Okay, well, I mean, yeah, this is just sort of like my characterization. It's not necessarily the only way of characterizing this, but like let's say this, like how they're used like in real world application. Yeah, so I mean, this is, okay. You can think of, like, say, the first 2 as being kind of inverse. So here, the idea is that maybe you don't have a huge amount of writes on your system. Your system is not write heavy, but then just serving the requests to clients that want to read data, maybe it's just, you know, overwhelming. So you just basically make, you know, asynchronous copies of that data. And then this, you know, so I think this is done, I mean, this is like, let's say, the original caching style, or correct caching structure. Or you can even think of this as being sort of the original, eventually consistent kind of system where you don't know when these updates are actually going to make it to these slaves. So I think like maybe if anyone ever worked with like, let's say these kind of like slightly lower budget web hosting providers where you make like some kind of an update to your configuration and then it's like, it takes like 5 minutes until it actually gets there. Most likely they have like 1 or 2 of these masters and then just took some time for, you know, the update to replicate out to one of the other systems.
Anybody that's used Twitter for a while has seen these kind of things happen on Twitter.
Yeah, I mean, it's understandable.
The
Because
replies come through before, like consistently a reply will come through before the original, things like that.
Yeah, and so I mean, these are huge, difficult problems to solve. Generally, I mean, the way that you solve it is just by saying, okay, well, we can't solve it, so we'll just try to make it not so bad. You know? So this is, I think, like the original way of sort of scaling out MySQL, because this has been built in from quite a while, I think. The second one, which is not mutually exclusive in the sense that you can, let's say, have, you know, a partition data set, which then you replicate down here for some scalability. But then this approach would be, like, let's say now you have a lot of writes, but you don't necessarily read all that data all the time. So imagine comments to Facebook posts. So I think, like, I'm fairly certain, I don't know how it is now, but it was the last I read about the way MySQL, or the way Facebook does things. They just have, you know, just a huge number of servers that have, you know, slices of the data set. And then the assumption is that generally you don't need to cross this boundary too often. And when you do, you end up like this. Because it's painful and it introduces all this complexity in this middleware, which ideally should have been in the database in the first place. So this is, you know, effectively the problem. It's that each of these servers doesn't know anything about the other server. It was never designed with the idea that half of its data lives somewhere else. So this would be sort of like a classic sort of sharding style This would just be sort of the classic, read-only slaves. And then you can merge these two to create multi-master rings, and then those rings can have slave offshoots, so you can do all sorts of interesting things. This would be, a whole bunch of different products. I think there are 50, and I'm sure today some new database company got funding, and now there's 51 on the market. A lot of them do this kind of middleware. So I think a lot of them will claim MySQL compatibility, but really what that means is that you support the MySQL protocol effectively. So a client talks to this database, it thinks it's talking to a MySQL database, but it really is something completely different. I think a lot of these solutions are like that. And then this would be basically MySQL cluster, which has been around for quite a while. The layer replication, which is, if you haven't read about the question there, if you haven't read about layer replication, I recommend taking a look at it. Did I do that? No. Okay. I recommend taking a look at layer replication because it's definitely the most similar, I would say, to our approach. But it's, in a way, it's a little bit less sophisticated because it's more bound to the existing MySQL because it actually uses InnoDB as opposed to the storage engine which we use.
You could see that as a plus.
It's depending on your needs, I guess. I think it makes it harder to build cool stuff, but then it makes it be better for backwards compatibility. So I think it would vary. So I don't know if that answered your question. More or less, did that answer your question?
Start if you have to write a lot. Can you replicate if you have to read a lot?
Yeah, I mean, effectively it's like copy your data so that you have more copies of it to read, or split it so that you don't have, so that you have more places to write it. So just take advantage of more of these servers. So, I don't know, anything else? People have like the feeling that they understand why the system is useful. I don't know if I've met that critical objective here. Yeah.
Well, I have a question. I hate for it to be a bad question. So to ensure Tomic-like operations, you run queries and transactions, correct? So I guess going back to the slide with the performance, is that you were talking about optimization? Was the reason that kind of at a smaller amount of requests or transactions, is that why it wasn't as fast in kind of optimization that you're going for, where you're using performance essentially on transactions?
No, the main reason, actually, if you want to look at, we have a slide, we have one where we compare MySQL cluster. Or sorry, no, you're asking about this one, right?
Yeah. Right.
Yeah, the point here, okay, no, the difference here is because, like, InnoDB is a mature, optimized product, and then it's designed to be really, really fast on one single server, right? So, in this case here, virtually all of the data would probably fit into the memory of that one server, and then it's going to be super fast. Whereas we have all of this sort of baggage in a sense of maintaining like a distributed system. But then the point is that once you get beyond the size of, let's say, the amount of memory that you have in that server, the performance drops off dramatically. And then once you get to this point here, now the data set is way bigger than the amount of memory that you have, and so you have problems of having to access disk. And then once you have to access disk for the process of your transactions, your performance is just done. Whereas with our approach, effectively we have disks, but they're not used to actually serve anything. Not in normal situations at least. So, if you hit so here we have a lower total capacity for one server, but then as you max that one out, you can just add new ones. So this is why, at least I see this as being a very good sort of cloud type environment, right? So let's say, instead of having to buy one $4 server here you can just sort of buy some 10-cent servers and then just add more of them as you need for different workloads variations, and then get rid of them when you don't need them. So I don't know if that answers your question, but
No, yeah, definitely.
one other thing just briefly about MySQL cluster, so that you have a slide. Basically, you can see, at least the way that we characterize it, is that basically this is the cost of elasticity and serializability. So our performance is anywhere from 50 to 75% of the performance of MySQL cluster, although this is just because it's academic written really quickly code that I'm trying to improve, so it's not fully optimized. I hope that we can get this a little bit closer so that we have similar, relatively close level of performance to MySQL cluster. But if you're building any kind of a serious system that needs transactions with MySQL cluster, or you just can't do it because you don't have a strong consistency level. I'll address it here in case you're curious about how to use the system or if you want to help out. Does that keep happening? Test? Okay. All right. Well, thank you. Thank you for listening.